Hello, community. A lot of questions I received from the beginner to artificial intelligence. How do you do this? Do you go from a text, from a book, from a paragraph, from a publication to a vector representation when you apply artificial intelligence? Now, this is the content of the video today. So we go now from a text in a specific human language, let's say it's English, in a specific region, let's say it's America, to a mathematical object of a vector. This is valued in any language ever on the planet. This here is a specific language that has a semantic context to a specific region. So the question is how to convert sentences from a human language to a number, a vector, a tensor, something we can use in artificial intelligence. So visually, we go from a body of text to a mathematical, numerical visualization or representation of the content of the text. You know, words have a meaning for us humans, but words have only a meaning in a context. So context means that the word stands close to other words, they have relations to other words in the sentence, and we have learned that words that are in a certain relationship with other words generates meaning. Think about people living in the Arctic. They have dozens of words for snow, and people in the desert have a multitude of words describing the sand and the wind and the heat. So you see, it depends on the context, and we need something that is context aware of the words, where the words are in a sentence and the semantic connectivity of words in a sentence. So to compute words for an artificial intelligence who has no idea of English, we assign a number to each word in order to apply mathematics to it. So to have a universal mathematical language. And the first using is statistics. We assign number to each word. Then we collect all numbers from our text in a vocabulary for translating now from the word to a numerical value. And if a word appears more often, we have another counter. Now, it is easy, but we want to apply AI to it. So let's have a closer look at this. There was a beautiful book, Vector Analysis in the good old times, that described geometric quantities that have a magnitude and a direction. And if you look at history, you had Descartes with his La Géométrie in 1637, where he more or less invented the Cartesian coordinate system that we know today. And a lot of other mathematicians, Euler, Cauchy, Ponson, Fourier, Riemann, Hilbert, they all had a significant contribution. And today we build on their results. So you need mathematics. And in particular, you need algebra. Algebra is, let's call it another branch of mathematics. And it tells you, hey, you know, if you have vectors, this comes from physics, we can add vectors together. We can multiply vectors with a scalar, and we can have an inverse multiplication of vectors. Can we? Yes, no, maybe. So you see, there comes a lot of topics, and mathematics invented a tool. And this tool in algebra is called group. And the group is the most powerful tool you will encounter in artificial intelligence. There are some axioms that define a group. It has to be associative, given some group operation star. Whatever this star is, it depends on the group. And you have to have an identity element, you have an inverse element, and the group is closed, of course. If you have those four properties, those four axioms that define a group, you can say that you are working with a group. And it's not just a vector, you can have many more generalization, and this is the power of this tool. And of course, we're going to talk about the concept of space. But for space, we build on algebraic structures such as a group, a ring, and a field. And then we are ready to say what is a vector space. Because for artificial intelligence, we have to have a deep understanding when we are operating with vectors, a matrix, a tensor, in a vector field, in a space. You have to know its properties, otherwise your operation would make no sense. Of course, modern algebra has evolved. In pure mathematics, you have category theory, homological algebra, group theory, algebraic geometry. Amazing. But what we need to focus is the easy thing. There's something called a space, a metric space. This is a set where the notion of a distance, called a metric, between elements of the set is kind of defined. And we have no metric space. If we have a more general topological space, we are looking for something that's called a nearness. Is something close by? Has it a similar meaning? You know, cosine similarity somehow comes close to nearness and semantic close operations. Now, if you want to know or learn in a very easy way about vector spaces, there's this beautiful YouTube channel I can really recommend. It's called Socratica. And here, from the particular video, what is a vector space, they give you a beautiful definition. You see here, you have algebraic elements, an abelian group of vectors, a field, a very specific algebraic expression of scalars, a scaled vector. You have distributive property, associative property, and you have a specific element. Now, coming from physics, and a lot of people have a kind of mind and they imagine vectors as specific elements in space. Okay, let's take this picture, why not? But at first we have a scalar. Think about if you say the temperature in degree, Celsius, Fahrenheit, whatever. It is a unit of measure. So it is simply a scalar. But you can have also physical and geometric quantities like a vector that require the specification of a direction and a magnitude. For example, velocity or the impact of a force are those examples in our real world. So if you look, those were the 16th, 17th, 18th century, maybe, Galois, the time of Galois and other mathematicians. You had scalar, vector, a low-dimensional space, the group theory came up, and then it evolved 20th century to the tensor algebra, high-dimensional vector spaces, group theory. A vector space can further be generalized to a module, but this would be mathematical algebra. This is not for us, but you see where our tools come from. So if you are in a position that you are at the very beginning of your career, it is a very good advice, study mathematics. However you do it at the university, self-study, mathematics provides the tool we use in AI, machine learning, deep learning, graph machine learning, everywhere you go. It's based on mathematics. So now that I have understanding of the tools, I told you that we use the words. The words in a sentence create meaning, and we take those words and we assign a value to it. Now, not surprisingly, it is not that easy. Because how we use or cut a word has a significant importance for the model we choose afterwards. So we are still looking at words, and we have to prepare the words not for us human, but for a machine. So how we do this? You can see there is a quantum chromodynamic. It's a word from physics. You can divide it up in the word quantum, that has a meaning, and chromodynamic has also a meaning. You can further divide it up in quantum, chromo, and dynamic. And you can assign numbers, numerical values to 3 word segments. Or you can even go further and you say, hey, this is a specific ending, this is a specific ending. So you divide up endings also. So you see the way you prepare your words, my goodness, there's a whole theory behind this. So we have to understand there is a particular tool also in artificial intelligence. It's called a tokenizer. So it is not always the words that we use, but we tokenize our text in different pieces. And it is not words of our sentences. Sometimes the tokenizer defines the objects. You split your words in 2. So if you're interested, I have a YouTube video on the idea of tokenizing. There's an introduction video. I have another video where I show you how to choose a tokenizer architecture, how you train a tokenizer on your text corpus. So there are ways that you can find an optimal textual representation for a semantic meaning on a domain knowledge given your text corpus. You can have a variety of predefined tokenizers for your text. There's this video. And if you're looking here for two very famous tokenizer, I have here a YouTube video on BERT. Oh, let's go back. BERT is here for word piece structure. Maybe you heard this. Or if you go for a byte pair, here we have BPE. So now that we have the mathematical objects, words, word pieces, like in BERT or byte pairs, to efficiently decode our human semantic text that we as humans understand, into new, and now maybe we call it semi-semantic objects, because those word pieces may not make sense to us, but it's optimal for a machine. Now, these semi-semantic objects, we transfer now into numeric values. So it is not words that we use, but some deeper structured mathematical objects. And from those numeric values that we create, we can then build up a vector, a matrix, a tensor, multiple tensors, high-dimensional mathematical objects, like I already showed you, a high-dimensional vector space. Beautiful. So, next part. What we do now with this vocabulary. We have now vocabulary, and if you look in this vocabulary file, you will notice that some of the word pieces there make no sense to you as a human. But this is how a vocabulary or tokenizer can be trained on your particular text. And if you have a medical text, your vocabulary will look completely different as if you have a text about, mathematics or physics or geology or astronomy. So, careful. For your specific text, there's a lot of tuning you can do. And then when we have our word pieces and we have the vocabulary defined, then we can use this vocabulary as an input to our natural language processing models. And of course, today we will have some transformer-based NLP models, but this will be the topic of my next video.